Hello everybody, this is the second video in our thermodynamics chapter, and in this lesson we're going to learn a little bit more about entropy so that you can better determine whether there's an increase or a decrease in entropy for a reaction. So I want to just go over a few concepts about entropy, give you some examples to look at. Some of this is on your glue-in, some of it you should add by hand to your notebook. So entropy is that thermodynamic function that increases as the number of energetically equivalent ways of arranging the components increases. That's what we were talking about the other day, where we want to use a much better definition than saying randomness, right? Or chaos or disorder. We want to be talking about the microstates, the number of ways we can arrange it, the number of ways the energy can be dispersed. And remember that we're being careful with our units, right? Joules are going to be showing up here versus kilojoules for enthalpy. So I love this picture because I think it tries to show you the difference between a macro state and a micro state. All 6 of these little strange containers over here have the same macro state. No matter what, there are 2 of these colorful dots on each side. No matter what, each picture, each arrangement has 2 dots on the left and 2 dots on the right. They are equivalent, right? But when you look more closely, can you see how the colors of the dots are different in each picture? So even though these all have the same macro state, they all have slightly different microstates. And the more components you have, the more space they have to spread out, the more complicated they are, etc., the more combinations you're going to have, right? Like we talked about with flipping the pennies, the different combinations you can have. So when we talk about something being random, what we're really talking about is having more ways to arrange things. And you may know this, sometimes it gets brought up in movies or books, things like that, TV shows, jokes, right, where the entropy is always increasing for the universe. The universe is always driving to get more and more and more entropy. One of the things that we will have to be careful of is understanding that being true for the universe as a whole doesn't mean that you can never have negative entropy. You can absolutely have negative entropy, but the universe is a bigger, broader thing to consider. Okay. Nature is always going to proceed in the direction that will result in the most probable combination with the most microstates, the most energy dispersal, etc. So you may have heard jokes about, oh, my room is so messy because of entropy. That's why my room always gets messed up. And while that is a joke, there is some truth to that, right? There's way more ways to arrange all the junk on your floor than there is for it all to be nicely, perfectly where it belongs, right? So the idea that things are going to tend towards more and more microstates, more energy dispersal, more disorder, right? That's actually quite true. So we can calculate delta S just like we calculate everything else, right? Final minus initial. Even though entropy is a weird concept, it still can be calculated in this very simple idea of final minus initial. So the standard entropy change is going to be the difference in our entropies when we're under those standard conditions. Remember, that's typically 25 degrees. But in theory, you should always be checking your data table to see what temperature those values are given at, but 25 is typical. So you've seen this equation before, haven't you? We've seen it written the same way, but with delta H, and then we've seen it written with delta G, and now you're seeing it with delta S, because it's all the same concept, isn't it? The difference between where we end and where we start is our delta. So if you are given delta S, or if you're given S values, you can find delta S, just like you've been doing with H and G. Now, one little thing we have to be careful about are the assumptions that we make, okay? You've been taught that the enthalpy of formation for an element, right, in that standard state is 0, because it doesn't take any energy to put it in the form that it's already in. The problem is that that concept does not translate to entropy. The standard entropy is not going to be 0, okay? It's going to be some kind of a positive number. Everything has some degree of entropy. So you cannot plug in 0 for elements when you're doing entropy calculations. There is one time where you might see something a little bit weird, where it shows you that you have a negative entropy. And that kind of throws people, because the idea is that everything has entropy. So how could something have a negative one? And it has to do with how we measure these values. We've kind of decided that the hydrogen ion is a reference point of 0, and we measure everything relative to that. So almost always things are going to have a higher entropy than that hydrogen ion. But every once in a while, you may have some other ions that are going to end up with less entropy than the hydrogen one. And so you may see a negative entropy for those ions. It's always something that if you get a negative answer, you should stop and really double check what you're doing, right? Make sure it makes sense. Almost always it's going to be a positive, but it also should never be 0 unless it's that hydrogen ion as our reference point. So let's do a practice problem. I've given you an equation. I've given you some delta S values. But what's interesting here is I'm not solving for delta S of the reaction. I actually told you that one. I'm solving for delta S for one of the chemicals. I want to know what the delta S is for the oxygen gas. It's not 0. Remember, the entropy is not going to be 0. So why don't you pause the video, give it a try, see if you can set up your equation, and calculate what that missing value would be. All right. How'd you do? So we have all S values, so we can use the subtraction method, products minus reactants. I know what the final is for the reaction. I had 2 moles of products over here, so make sure you put the 2. Over here I have 2 moles of nitrogen monoxide, and I only have 1 mole of oxygen. So I'm solving for delta S of oxygen. Now, one thing that you may notice a lot, which is super annoying, but I can't really fix it, is that we will often see that entropy has the units of joules per Kelvin, and then sometimes like this problem, you're going to see joules per mole Kelvin. And it's a little bit hard to explain why. It has to do with some of the standard practices for how we calculate these. If we're calculating them for 1 mole of something at a time, then the mole would not be necessary, right? But then you're not always calculating for 1 mole, so sometimes we start putting in the mole there, and I wish we would just always be consistent, but unfortunately they aren't. So I will mix and match it together so that you get used to seeing it both ways. Not a huge deal in the long run. In terms of the units, what they're really going to be after is whether you notice the entropies in joules and enthalpies in kilojoules. They will often tell you somewhere in the problem if they want it to be joules per Kelvin or joules per mole Kelvin. So I would not stress out about this. That kind of an answer is going to happen a lot, where why isn't it consistent? Well, just for historical reasons, right? We don't always do things the same way over time. Some things become standard practice, some things don't. Switching gears, let's go back to some concepts for a minute. Let's think about some of the things that would result in an increase in entropy. So having our products in a more dispersed arrangement, and that can mean a variety of things. For example, it could mean going from a solid to a liquid to a gas. You're going to have way more arrangements as those particles can spread out. And you can see here's an example. Liquid water to gas. Now, you should notice that the Kelvin is there, right? Because this is temperature dependent. So that's something to think about as well. Another way you can have a more dispersed arrangement would be through dissolution. When you have a solid that is dissolving, maybe you dump some salt into water, for example. Usually, you're going to have an increase in entropy. Those particles are going to be more mixed together, a lot more ways for them all to be arranged. So things that become aqueous tend to have an increase in entropy. Sometimes it's dramatic. That's almost twice, isn't it? Now, one of the things College Board has started doing more recently is giving examples where you would anticipate an increase in entropy, you do a bunch of calculations, and you find out there's actually a decrease in entropy, and people get really flustered, and they think they did a calculation error somewhere. So I always encourage you to stop and think about what's happening physically. When you have something like an aqueous solution, you have some ions mixed with water. Physically, we have to remember that you might get water molecules surrounding those ions. That's called a sphere of hydration. The water is forming a shell around the ions because we have the charges, right, those partial charges on the oxygen or the hydrogens attracted to the charge on the ions. And that can actually result in a decrease in entropy. So whenever you get an answer that seems backwards, yes, obviously stop and double check you haven't done something wrong. But if you're looking at your numbers and they seem to make sense, then start thinking physically, oh yeah, what might be happening with the particles themselves? Maybe that explains my decrease in entropy. Another example would be having more product molecules than reactant molecules. For example, look at this decomposition reaction. We started with one thing, and we ended up with 3 separate particles and 2 different types of particles, right? A lot more ways we can make arrangements over here. Increasing that temperature. Now everything's moving faster, right? A lot more ways to spread out, a lot more arrangements. Having more degrees of movement. So one thing to understand is that there are lots of types of movement. We are used to thinking about things just moving side to side, zooming around faster and faster as they heat up, or slower and slower as they cool down. But that's not the only type of movement. Translational movement is only one type. They can also rotate. They can also vibrate, right? There's lots of ways things can move. I love this example because we can see that even within a single molecule, there can be things to consider that would result in changes to the degree of movement. On the left, do you see how that compound has those two hydroxide groups on the end? That chain is flexible enough to bend around, and we can end up with some hydrogen bonding happening here between one end and the other. One end is donating the hydrogen to the hydrogen bond, and one end is receiving it. Hydrogen bond donator, hydrogen bond acceptor. And look what happens to the overall shape. Now it can't move around nearly as much. This ring shape does not have as much degree of movement. This would be a decrease in entropy. Sometimes it's the complexity of your products that are increasing the entropy. And there's several ways they can be more complex. A single argon versus a nitrogen monoxide. Nitrogen monoxide is more complex. There's more going on. I have two different atoms, right? Two different elements, and there's bonds happening, sharing of electrons, and a lot more things going on. And look at the entropy. One of the things that we have to be careful of is not mixing and matching the concept of larger, more complex with assuming we mean molar mass. Molar mass might be one component of it, but it doesn't always mean the heavier thing. So look at our argon and nitrogen monoxide example. Argon is heavier, but nitrogen monoxide's complexity outweighs that. No pun intended there, okay? But that's going to result in more entropy. The complexity is huge here compared to a single argon. The reason this complexity matters is because the more energy levels you have, the more arrangements of all that energy can be within those various states, which means it's more dispersed and there are more arrangements, more entropy. Molar mass can play a part, but we want to make sure that we are not ignoring the complexity factor. When we're comparing molar masses in terms of entropy considerations, we should be looking at things that are kind of similar to each other. We want to kind of compare apples and apples. If you look here, these are all single elements, right? All these noble gases, those are kind of comparing apples to apples. Comparing argon and nitrogen monoxide is like comparing apples and oranges, right? That's not the same. So be careful with molar mass problems. The larger your molar mass, the larger the entropy. Sometimes people say that that seems backwards to them because they think, but if it's bigger, they take up more space, so there's not as many places for them to be. So to them, they think that's backwards. The problem is that you're not thinking about the energy levels within the atom or molecule. So let's look at some examples here. The larger your molar mass, the closer together your energy levels are. So the top would be a small thing. See how far apart these levels are? And the bottom, see how close together they are? This would be a larger massed substance. The closer together your energy levels, the more options you have to disperse throughout them. So on the small one, maybe there's only two ways that it can happen. Maybe the energetics only allow two combinations. But when our energy levels are so close together, maybe I can have 5. So the larger molar mass thing has more choices, more microstate arrangements within those energy levels, within those energy states. All right. Moving on a little bit, let's take a bigger look at entropy. Let's kind of zoom out for a minute, way out, and think about the entropy of the universe for a second. So when we're doing reactions, we always tend to think about the system and surroundings from a small perspective, like the chemicals inside the beaker. But in reality, the surroundings is the entire rest of the universe, okay? So sometimes it can be helpful to think about the universe as a whole to help us understand how the change to entropy of the system connects to the surroundings, okay? The total entropy change of the entire universe must be positive in order for a reaction to be spontaneous. If it's reversible, like an equilibrium, it would be 0. No change, that's why it's allowed to happen both ways. More normally, it would be irreversible, and we'd see a positive delta S for the universe. We can still have a negative entropy for the system as long as the change in the surroundings can overcome it. So when we think about the universe, that's really saying system plus surroundings. So if the entropy of your system is decreasing, then the entropy of your surroundings needs to increase by an even larger amount. We have to end up with S universe positive. So in order for the entropy of the universe to be favorable, to be positive, when our system is negative, do you see how you're going to need a really big positive surroundings? Not just positive, but it needs to be positive and larger than the system. If your surroundings is negative, maybe there's a decrease in entropy of the surroundings, then your entropy of the system change needs to be positive and bigger than whatever this negative number was, so that we can end up with a positive, favorable delta S universe. There are some connections we can make to convert between enthalpy and entropy and to help us get from system surroundings to universe. So I'm going to show you some little equations you can substitute a little bit to help you make some rearrangements that can be helpful to you. So the first thing we have to understand is that the entropy change to the surroundings is proportional to the heat being gained or lost. So remember, the heat is going to be Q. Also remember that sometimes it's hard to measure the surroundings versus the system. So the thing that's helpful to remember is that the surroundings will be equal and opposite the system. We learned that in the thermochemistry chapter. Another part of this is that we need to understand that the entropy change in the surroundings is inversely proportional to the temperature. So what that means is that the impact of our enthalpy is going to be more noticeable at lower temperatures. If you're at a really low temperature and some heat is released, that's going to feel like a really big change. If you're at a hot temperature and a little bit of heat is released, it's not going to be as impactful. So this ends up giving us an equation where the change in entropy of the surroundings is equal to negative Q system over T, directly proportional to Q, inversely proportional to T. And because we're working with problems that are simplified, we're not going to have crazy changes to volume or crazy changes to pressure. Remember, we can say that Q and delta H are the same. So this allows us to say that the change in entropy of the surroundings is equal to negative change in enthalpy of the system over the temperature that it's occurring at. And this can let you mix and match things together in creative ways. In my opinion, I think that's what makes things like thermodynamics really hard, is that they feel overwhelming when you learn just a couple of equations and then all of a sudden you're doing a problem where you're mixing and matching them together. But that's the goal. That's the task you've been assigned. The task is to learn how to take simple equations and mix and match them and mush them together. Okay, that's the skill they're assessing you on. They are not assessing you on whether you memorized the 4 equations I gave you. They're assessing you on, is your brain creative enough to mix and match them? We need repeat exposure to these things. We need repetition for it to come more naturally and quickly. It is not likely that most of you are going to be super good at this right away because it's new and it's different and it's creative. We're not used to being creative with our math. And that can be uncomfortable for some people because sometimes people like math because they feel like they don't have to be creative. They feel like they can be a little robot on autopilot. And that doesn't work here. This is application of math, right? So sometimes what might look like a new equation to you is not new. So for example, we learned that delta S of the universe is the system plus surroundings. This equation down here is nothing different. It's the same thing. It's just that instead of trying to measure the change in entropy of the surroundings directly, well, if I already know delta H and I know what temperature I'm at, I can just substitute and measure my system here, can't I? That can be very powerful to us. It allows us to measure things that we may not be able to otherwise. It allows us to calculate things we may not have been able to otherwise. So really get the perspective and really embrace that you're gonna have to get some creativity here. More practice problems will help, right? The more exposure you can get, the more practice you can get, the better. You could start a little cheat sheet where you write down all the arrangements you come across. But it's going to be hard to keep that up all year long. That's going to be a really, really big cheat sheet, right? It's going to have so many arrangements. It is better to understand what the equations are telling you, and it's better to understand the concepts and be able to combine them on the fly. That's going to be much faster in the long run. You're going to have a better understanding in the long run, okay? All right, everybody. Well, now you know way more about entropy than you did before. You'll be able to start doing some math related to entropy a little bit more than before. And then we'll have one last lecture. We're going to go back to Gibbs free energy and start doing more involved calculations with Gibbs. Okay? All right, everybody. That is it for this lesson. I hope that was helpful. Bye.